This is continuation of our discussion on the geometry of different complex valued functions. In our last discussions, we studied what are linear transformations and what are their geometrical properties. So in particular, we considered some subsets of the z-plane and we studied the effect when we apply linear transformations on them in the w-plane. Now we are going to study some other kind of complex valued functions. So these are complex valued functions, so which are nth power and nth root functions. Now these functions are basically special cases of a broader class of complex valued functions, which are power functions. Now we have seen power functions in calculus and in real analysis, okay, where we studied what are real valued power functions, which are functions of the form x raised to power alpha, where alpha is a fixed real number and x is the real variable. Now these functions are not only simple to handle geometrically and algebraically, but also have some interesting geometrical and algebraic properties. So that's why mathematicians are always interested in studying these kind of functions. Now, when we transfer ourselves to the complex case, then we have the following complex valued power functions, which are functions of the form z raised to power alpha. Now, z is the complex variable here, and alpha is any fixed complex number. Now, it could be any number of the form, so iota, 1 plus iota, 100 plus 2 iota, it could be 100, it could be pure real 100, or it could be pure imaginary like iota. Now, if we consider alpha to be in complex number which involves iota, then these are very complicated cases and they will be studied later. But now on, we are going to focus when this alpha is integer. And not just only integer, but a positive integer, okay, alpha is n, and 1 over n, where n is a positive integer. Okay. Now, in this discussion, we are going to choose a very special value of n, that is n is equal to 2. And we are going to study these functions, which are the square function and the square root functions, and we will discuss different geometrical properties of these two functions. Now, starting from the functions f of z is equal to z square, if we want to study these functions in a simplified way, then we should choose the exponential form of the complex numbers. Now, it will make our calculations easy, but there is always a restriction that z is not allowed to be 0, because there is no exponential form for the complex number z is equal to 0, because there is no specified value of the argument. Okay, so in this case, if z is equal to r e raised to power iota theta, and if we apply this mapping z square, then it becomes r square e raised to power iota theta. Now, we are using these exponential form in the z plane, and if we also consider the exponential form in the w plane, that is, if we take w is equal to phi e raised to power iota phi, then this mapping become, okay, so comparing this form r square e raised to power iota 2 theta with this form rho e raised to power iota phi, so this gives us the following result, that rho is equal to r square and phi is equal to 2 theta. Okay, so this tells us about the behavior of this mapping z square. So for example, it tells us what will happen with the modulus of this complex number. It will be squared. So for example, if r is equal to 0.5, the image in the w plane of that complex number will have modulus 0.5 square, which is 0.25. Okay, similarly, if r is equal to 1, it will be mapped to a complex number in the w plane with modulus 1. Okay, now let's choose a very particular value of complex number where theta is equal to 60 degrees. And in this case, we choose a complex number where r is equal to 1. Okay, so this is z, r is equal to 1. So this is e raised to power iota theta. So this is the value of theta. And in particular, this value of theta is 60 degrees. So r is equal to 1. So it will be mapped to a complex number in the w plane where this modulus is 1. Now what will happen with the argument? So we can see that if we apply this mapping on r e raised to power iota theta, then in the w plane or in the image of this complex number, has argument 2 times the argument of z. So in this case, in this particular example, if theta is equal to 60, then the image f of z has theta 120 degrees. Okay, so this is phi. Okay, so this is phi, which is equal to 120 degrees. And since r is equal to 1 in this case, and r square is 1, so that's why rho is also equal to 1. And similarly, we can calculate other examples where we have different values of r. So observe that if r is greater than 1, then in the w plane, after applying this mapping z square, it will be further away from the origin. It will go away from the origin. And if r is less than 1, then after applying this mapping, it will get closer to the origin, because when we squared a number which is less than 1, it will become more, okay, it will be more smaller, okay, than the original number. But the numbers for which r is equal to 1, they will be mapped on the numbers for which this modulus is 1. Now let's just restrict ourselves to a very particular domain. So the function is the same, z square, but the domain is restricted to this set A. Now we can sketch this domain in the complex plane. So it consists of all the complex number for which the modulus lies between 0 and 1, and r is not allowed to be 0, and it is less than or equal to 1. So whatever this subset of z plane is, it lies inside this unit disk. And now let's see what will be the what are the conditions on the argument. So the argument lies between pi by 2 and minus pi by 2, and minus pi by 2 is not included, so there is a dashed line here. So everything inside this half unit disk. Now we have shaded these two regions differently so that we can observe what will happen after we apply this f of z is equal to z square on this half disk. Now let's first calculate the image. So the image of this A becomes this set B. So it consists of all the values in the W plane where rho lies between 0 and 1. So since R lies between 0 and 1, so if we square them, then we get numbers that lies between 0 and 1, because if R is equal to 1, R square is 1. And if R is any number between 0 and 1, then square of that will also lie between 0 and 1. So that's why this rho lies between 0 and 1. Now let's see what will happen with the argument. So when theta lies between minus pi by 2 and pi by 2, so when we apply z square, then it will be doubled. So pi by 2 becomes pi, minus pi by 2 becomes minus pi. Okay, so for example, if we have a number that lies here in this half unit disk, and when we apply this z square, then so for this complex number, theta is pi by 2 and r is 1. So when we apply this z square, so theta becomes pi and r becomes so r square, which is again 1. So this is mapped onto the following number. And similarly, if we choose any other number, so if we choose this number, okay, so where theta, let's call it theta prime, is pi by 4 and r is 1, then it will be mapped onto a number where theta is pi by 2 and r is once again 1. So that's why it will be mapped onto this number. So in general, we can see that this squared shaded area will be mapped onto this shaded area. Okay, so let's call it shaded area 1. So it will be mapped onto this shaded area 1. And similarly, this grayish area will be mapped onto this grayish area. So this region 2 will be mapped onto this region 2. Now let's talk about the inverse of this function. Okay, so the inverse of this function, let's guess, so it will be the square root. Okay, so we are squaring, then the inverse function will be the square root, and we will, of course, afterwards we will prove that why they are inverses of each other. Now let's first see what is the square root of this complex number. So what will happen? So the modulus will be square rooted and the angle or the argument will be halved. Okay, and of course if we write down the argument, okay, so phi is basically the argument or the principal argument, so this is the form of this square root function. Okay. Now, remember, when we calculated the square root of a complex number, then we observed that there are going to be two outputs of the square root of a complex number. But here, it is a single valued function. So what is the difference between these two arguments? So over there, we use the fact that theta is allowed to be any argument. Okay, so theta could be replaced with theta plus 2k pi. And when we varied k, then we get different square roots of a complex number. Now over here, we are not allowed to add or subtract multiples of 2 pi. So it is the argument of the complex number. So that's why it is a single valued function and not a multi-valued function. And the output is always going to be one number. And we can also observe that what will happen when we apply this principal square root function. Okay, so this modulus will be square rooted and the argument will be halved. So once again, if we are applying on this number, so let's say this number is w is equal to 1 e raised to power iota. Okay, so theta, where theta is basically 60 degrees. Okay, so when we apply this principal square root function, then square root of 1 is 1 and half of this 60 degrees 30 degrees. So that's why it will be mapped onto this number. Okay, so this is g of w. Okay, now of course we can calculate the composition of f and g, and if these two compositions satisfy these conditions, that g composition f of z is z and f composition g of w is w, then we say that they are inverses of each other. Now I am leaving this as an exercise for you to check that f and g satisfy these two conditions. Now if we color or set A, okay, and consider the effect of this mapping z square on this half disk, so that's what will happen. Okay, so these complex number in the green area will be mapped onto complex numbers in the green area, and the complex numbers in this orange region will be mapped onto these complex numbers, and similarly other regions. Okay, so the shades of this red will be mapped on these shades of red, and these shades of blue will be mapped onto this. So this tells us in a more precise way what will happen with the complex numbers when we apply this mapping z square. And of course, when we apply this mapping g, which is the inverse of this function z square, then everything will be reversed. Okay, so we are moving then from this complete unit disk to this half unit disk when we are applying this principal root function. Now let's consider this mapping z square and try to study the geometrical properties of this z square. So when we say geometrical properties, in other words, we are going to choose some subsets from the z plane and we are going to study what will happen with them when we apply z square on them. So in particular, we are going to choose lines which are parallel to the y-axis or the imaginary axis, and lines which are parallel to the real axis, and we want to study what will happen when we apply z square on them. Now our claim is when we apply this z square onto lines which are perpendicular, okay, so these red lines perpendicular to this real axis or vertical lines, then they will be mapped onto these red parabolas. And if we apply this mapping z square to these horizontal lines, in other words these green lines, they will be mapped onto these green parabolas. Now let's see how to prove this claim. So starting from this mapping z square, we can write down their components in the following way. So if we have a complex number in the z plane, so it is given in the form z is equal to x plus iota y. And if we calculate its image in the w plane, then it will be some complex number f of z with components u plus iota y. Now we can calculate this u and v in terms of x and y in the following way. So f of z is equal to x plus iota y square, and we can simplify this thing, x square minus y square plus iota 2xy. Now comparing this with u plus iota y, this tells us that this is u and this is v. So u is equal to x square minus y square and v is 2xy. Now if we consider a vertical line defined by the condition x is equal to a, then using this x is equal to a into u is equal to x square minus y square, it becomes a square minus y square, and v becomes 2ay. Now if we consider the case a is not equal to 0, and of course later on we will study when what will happen when a is equal to 0. Now in this particular case, if a is not 0, then y becomes v over 2a. Now putting or using this value in u is equal to a square minus v square, we get this expression. Now this expression can be further written in the following way: u minus a square is equal to minus 1 over 4a square and v square. Now this is just a translation along u-axis of a parabola. Okay, so parabola with vertex a square and horizontally opening to the left. Okay, so it is oriented horizontally and opening to the left. Okay, now let's see if this is our map x is equal to a. So this is the line, vertical line. Now this is mapped onto this parabola. So the vertex of this is basically a square. So let's say this is a square. So it is parabola of the following form. Okay, now let's see in detail what is really happening. Okay, so this is our line x is equal to a, and this is the parabola with vertex a square. Now consider this part of the discussion where v is equal to 2ay. If we consider a is greater than 0 and y is greater than 0. If a is greater than 0 and y is greater than 0, then v is greater than 0. So definitely if we consider the portion of the line for which y is greater than 0, in other words above x-axis, so this portion, so if we consider this portion, so this portion has y is greater than 0. Now this portion of the line will be mapped onto the points where v is greater than 0, in other words above this u-axis. And similarly, if we consider this portion where y is less than 0, then it will be mapped onto the portion where this v is less than 0. And of course, this is the case when a is greater than 0. And similarly, we can study the cases where a is less than 0, and we can study which portion of the line will be mapped onto the upper part of the parabola and which portion will be mapped onto the lower part of the parabola. Now let's consider the image of horizontal line. Now horizontal line is given as y is equal to b. Now if we want to study its image, once again we use u is equal to x square minus y square. Here y is b, so it becomes x square minus b square, and v becomes 2xb. Now once again we impose the condition that b is not equal to 0, and calculating the value of x gives us the following equation. Now once again we can write it down in the following way: u plus b square is equal to 1 over 4b square v square. Now this is once again equation of a parabola. Now the vertex has been translated along the u-axis to minus b square, and of course it is opening in the opposite way, so it is oriented horizontally but opening to the right. Okay, so for example, if this is the line y is equal to b, then it is mapped onto the parabola of the form this, and this is the vertex of this parabola. Now on the same lines we can study that which portion of the line will be mapped onto which portion of the parabola. So for example, if this is the line y is equal to b, and we consider the case b is greater than 0, so the line is above this x-axis or the real axis. And if we consider once again this equation, so here b is greater than 0. If x is greater than 0, then v is greater than 0. In other words, this portion of the line, so this portion of the line for which x is greater than 0 will be mapped onto the parabola where v is greater than 0. And if we consider the portion of the line for which x is less than 0, it will be mapped onto the parabola where v is less than 0. Now in general we have the following picture. So these vertical and horizontal lines are being mapped onto these parabolas. Now we can see that elements which are in the first quadrant are mapped onto quadrant 1 and quadrant 2 by this map z square. So in other words, we can say that if we consider this rectangle where x lies between 0 and a and y lies between 0 and b, then it will be mapped onto the region bounded by top halves of these parabola. So this is first half of this parabola, so this is continuing in the other way, and this is the second parabola, okay, so continuing in the other way. So these are the top halves, and this rectangle will be mapped onto this portion. So if we are given the vertices of this rectangle, so a iota b, a plus iota b, so they will be mapped onto a square minus b square, a square minus b square plus iota 2ab, and these lines will be mapped onto these parabolas. Okay, so similarly these parabolas. Okay, and now consider the case which we avoided. Now if we consider x is equal to 0, then this is mapped onto this. So once again, if you consider x is equal to 0 in the x square minus y square expression, then it becomes minus y square, and v is definitely 0. And we can see that it will be mapped onto negative real numbers. And if we consider the case where y is equal to 0, then once again using the same equation, u is equal to x square minus y square and v is equal to 2xy. So v becomes 0 and u becomes x square. So these are positive real numbers. So the points which are basically these lines where y is equal to 0, so these are mapped onto the positive portion. So these are the positive portion, and the points which lie on this portion, okay, so they will be mapped onto the negative portion. So in this session, we started our discussion on some very special power functions, which are complex valued functions of the form z raised to power n and z raised to power 1 over n. And in this session, we chose the value of n to be equal to 2, and we studied the geometry of z square and the principal root functions. We will continue our discussion, and we will discuss in our next session the geometry of these mappings z square and z raised to power 1 by 2. And of course, later on we will study the geometry of z raised to power n, the n power functions and n root functions.